Here is my favorite question from Zumdahl. Well, they're all my favorite, but this is one of my favorite. This is from chapter 14. Can't remember exact number here, but lovely little picture. I've got two probes sticking into my aqueous solution here. Again, we're assuming everything is aqueous. I've got a conductivity probe, a simple light bulb. We've used this in class. And I've got a pH probe. Okay. Notice the light is glowing brightly. What does that mean? That means that this solution is an excellent conductor. And there's only two ways we're going to get a solution to be an excellent conductor. Either a strong acid that is completely ionized. So, for example, remember our strong acids, HCl, HBr, HI, HClO4, HNO3, and sulfuric acid, at least for its first ionization step. All right. Right away, we look down here, okay, and we see we do have HCl. Great. Okay. The second criteria is pH. pH is 4.6. Okay, that's an acidic pH, so our substance has to be an acid, but the pH is not what we would expect if we had a strong acid. If I had a 1 molar solution of HCl, for example, okay, a 1 molar HCl solution of HCl would have a concentration of H plus equal to 1 molar, right? It would be completely dissociated. The pH would be a very low 0.00. Okay, so our pH is not at 0, so we can immediately rule HCl out. All right, good. So two things we've got to come up with. We've got to come up with an excellent conductor, okay, and we've got to come up with pH. Okay, I got ahead of myself. Other way to have an excellent conductor, ionic compound. Ionic compounds that dissolve in water completely dissociate. So already ruled out one. So take a look. What do we got? Here's an ionic compound. Sodium hydroxide. What's the problem? Sodium hydroxide is not going to work for us. Sodium hydroxide, when it dissolves in water, is going to produce lots of sodium ion and lots of hydroxide ion. This solution is going to be an excellent conductor. Lots of ions, but it's going to have a very high hydroxide ion concentration. Matter of fact, we know the hydroxide ion concentration would be 1 molar. Therefore, the pOH would be 0, just the opposite of what we had up here. And the pH is going to be what? The pH is going to be 14. All right? So even though this would satisfy the conductivity, no way does that satisfy the pH requirement. So we can rule out NaOH. Who else can we rule out? Let's see. Now we're left with, let's see, we've got two ionic compounds left, right? NaCN, NH4Cl, ionic compounds, and we've got a weak acid, a weak base, and another weak acid. So, weak acid. Well, weak acid would potentially serve the pH, right? HCN, weak acids, would dissociate slightly to produce some H plus and Cn minus. What's the problem here? Sure, that reaction might get us the pH that we are looking for. It would certainly be acidic, but only going to produce very few ions. Very few ions. This solution of hydrogen cyanide is not going to be a good conductor. Not a good conductor. It would be a very weak, if at all, electrolyte. We're looking for a strong electrolyte. Similarly for HF. HF and HCN would both fit in the same category. They are both weak acids. They could meet the pH requirement, but no way could they meet the conductivity requirement. Okay, so we can throw them out. Oh, let's take a look at ammonia. Ammonia, I hope everybody recognizes, is not a weak acid, but is a weak base. Ammonia will pick up a proton, form ammonium ion, plus hydroxide. A solution of ammonia is definitely going to be what? It's definitely going to be pH greater than 7. So this would not meet the criteria on two situations. It's going to produce a pH greater than 7. We can immediately throw it out. It also is not going to give us very appreciable conductivity. Okay. Finally, that leaves us with ammonium chloride. Excuse me. Okay. That leaves us with two ionic compounds, sodium cyanide and ammonium chloride. So now we've got to think of these two. Both of these would be excellent conductors because they would both be ionic compounds. They would both dissociate to produce large concentrations of ions. They would both make solutions, aqueous solutions, that were excellent conductors of electricity. So they would both make the light bulb glow brightly. Which one of these solutions is going to be acidic? Well, I hope you can look at those and say to yourself, okay, the ammonium ion is the conjugate base of ammonia. Notice up here. So ammonium ion is going to act as a weak acid. Some of those ammonium ions produced are going to undergo ionization to form hydrogen ions, right? So pH is going to be less than 7, but because this is a weak acid, it's not going to be very low, so this would certainly meet the criteria. The other one, on the other hand, cyanide, would do just the opposite. Cyanide, being the conjugate base of the weak acid HCN, is not going to produce hydrogen ion, but is going to produce hydroxide. If the pH had been above 7, but not significantly above 7, cyanide would have been a possibility. So our mystery substance is ammonium chloride. Ammonium chloride would give us ions for conductivity, going to give us just the hydrogen ions we need for pH equal to 4.6. All right? I hope this little discussion helps you understand how to use some chemical logic without necessarily having no calculation. No calculation required. Process of elimination allowed us to come up with the realization that the only compound that could give us the combination of conductivity and pH would be ammonium chloride. All right? Excellent. Beautiful question.